Alright, hi Year 12s. This is a video for you to learn how to do empirical formula via combustion data. Alright, what you need to know at the beginning is, you need to remember the definition of the empirical formula and what are the steps to find the empirical formula. If you haven't done that, you can pause the video and you can go read up on how to do that again before we continue. Alright, so the empirical formula by combustion data. Just like the empirical formula we did in Year 11, the goal is still to find the number of moles of each element so that we can compare them against each other so that we can work out the empirical formula. Remember, you would find out the number of moles of each element and then you would divide it by the smallest, and that would give you the ratio of atoms for each element. So, instead of being given data about each element like last year, like the percentages or the masses of each element, this year we are going to be given data about the substance after it has been combusted. Combusted just means burnt in oxygen. So, for example, we have hydrocarbons. Hydrocarbons are made up of carbon and hydrogen with some sort of ratio of X carbons to Y hydrogens, right? And it's burnt in oxygen and it will form X amount of carbon dioxide and Y/2 amount of water. Okay? So, if we are given information about the carbon dioxide and the water, we can work out the number of moles of carbon dioxide and water. And through the moles of carbon dioxide of water, we can work out then the number of moles of carbon and hydrogen. Alright? So the number of moles of CO2 will lead to the number of moles of carbon via a 1-to-1 carbon dioxide to carbon ratio. The number of moles of water will lead to the number of moles of hydrogen via a 1 water to 2 hydrogens ratio. So let's go see an example of that. So here is a question. Hydrogen is completely burnt in air. 2.46 grams of the hydrocarbon forms 7.45 grams of carbon dioxide and 3.81 grams of water. So let's go work that out. So first of all, we need to work out the number of moles of the things that we do know. The number of moles of carbon dioxide is one thing that we know, right? And the number of moles of carbon dioxide will be equal to 7.45 over the molar mass of carbon dioxide, which happens to be 44.01. Okay? This will get you the number of moles of carbon dioxide, which will happen to be 0.169 moles. Okay? The number of moles of carbon, that's fairly straightforward. Carbon dioxide, that's fairly straightforward. So now we need to work out the number of moles of carbon from the number of moles of carbon dioxide. Now, since there is one carbon in every carbon dioxide, the number of moles of carbon will be equal to the number of moles of carbon dioxide times a 1-on-1 ratio. So therefore, that's 0.169 mole again. Therefore, we've got the number of moles of carbon. We can move on and try and work out the number of moles of hydrogen. The number of moles of hydrogen will be solved by the number of moles of water. So we take the 3.81 grams of water divided by the molar mass of water, which is 18.016, and we get how much? 0.212 moles. All right. Now, we've got the number of moles of water. Now we need to work out the number of moles of hydrogen from the number of moles of water. So, since there are 2 hydrogens for every water molecule, therefore the number of moles of hydrogen is equal to the number of moles of water times 2-on-1. Okay? Let's think about that. For every 1 water molecule, we have 2 hydrogens. So 1 water is equal to 2 hydrogens. Okay, so we double that. That ends up being, what's that? 0.424 moles. Right, so those are the 2 moles of carbon and hydrogen. Now we can move on and work out the ratio between them. Okay, so we have carbon and hydrogen. We have the number of moles of each, 0.169, 0.424. Okay, what do? We divide it by the smallest, which happens to be the carbon. So 0.169 over 0.169 and 0.424 over 0.169. This is 1. And the other is 0.424 divided by 0.169, 2.5. Okay, now, what do we do when our ratio is 1 to something which is 2.5? Okay, remember you have to have this is the simplest whole number ratio, so we need to multiply these numbers out by something to get them to a whole number ratio. Since this is a half, we multiply both by 2, gets you 2 to 5 ratio. So therefore, the empirical formula of this substance is C2H5. All right? So, that's the process there. Okay? Let's go back to the notes. So, we can work out the empirical formula from the carbon dioxide and the water, working out the carbon and the hydrogen. That's for hydrocarbons. However, for organic substances, which have carbon, hydrogen, and oxygen, and other elements if possible, or if necessary, it looks something like this. The organic substance is CXHYOZ, okay, where X, Y, and Z are certain numbers. Right? It's going to be burnt in oxygen. We've got a number of, we have X CO2s and Y on 2 H2Os. Okay? The number of moles of carbon dioxide will again lead to the number of moles of carbon via a 1-to-1 ratio. And the number of moles of water will again lead to the number of moles of hydrogen via a 1-to-2 ratio. However, we still need to work out the oxygen. However, the number of moles of oxygen cannot be solved directly. This is because the oxygen could have come, so that means the oxygen from the carbon dioxide and then oxygen from the water could have come from the organic substance or the oxygen gas that was burnt in. So the number of moles of oxygen must be solved via mass substitution of the carbon and the hydrogen components of the organic substance. So therefore, I can work out the mass of oxygen is equal to the mass of the organic substance, subtract the mass of the carbon and the mass of the hydrogen put together. Then once I have the mass of oxygen, I can work out the number of moles of oxygen. So let's go try that. Okay, so here is another question. An organic substance made of carbon, hydrogen, and oxygen is burnt in excess oxygen. 19.8 grams of the substance burns to form 43.5 grams of carbon dioxide and 23.74 grams of water. All right, just in case you can't see those decimal places, that's one there, that's one there. Okay, so that's one there. So let's go work this out. Right, the carbon and the hydrogen, we're going to do exactly the same as we did before. So the number of moles of carbon dioxide is equal to 43.5 over 44.01, which happens to be 0.988 moles. This gets me the number of moles of carbon because it's going to be equal to the number of moles of carbon dioxide. And I'm done for the carbon. Now we do the water. The number of moles of water is equal to 23.74 over 18.016. Where did I get that 18.016? It's from the molar mass of water. And the moles of water is 1.32 mole. Again, we get the number of moles of hydrogen from the number of moles of water times 2 on 1, which would then be 2.64 mole. Now, we've worked out the carbon, we've worked out the hydrogen, but we now need to work out the oxygen. Now remember, the oxygen in the carbon dioxide and the water could have come from the organic substance or the excess oxygen that we burnt it in. So we need to work it out by mass substitution. So we need to work out then the mass of carbon and the mass of water, the mass of hydrogen. So the mass of carbon will be equal to 0.988 times 12.01. Okay, again, this is the m is equal to n times big M. All right, 0.988. Actually, let's go get this right. Let's do this properly. 43.5 divided by 44.01 is equal to 0.988. I'm just doing this in my calculator properly so I don't round too early. And I get 11.87 grams. I'm going to save that as a letter A. I now have to work out the mass of the hydrogen. Okay, so 23.74 divided by 18.016 times by 2, and then times it by 2.64 times 1.008, and that's 2.66 grams of hydrogen. I'll save that as B. Right, so now I have to work out the mass of the oxygen. The mass of the oxygen will be equal to the mass of the organic substance, subtract the mass of the carbon, plus the mass of the hydrogen. So, what's the mass of the organic substance? It's 19.3 grams. So 19.8 grams. Subtract the mass of carbon, 11.87, and the mass of hydrogen. Can you see what I've done wrong there? Brackets are important. So, I do 19.8 subtract bracket A plus B bracket, and I get 5.27 grams of oxygen. I can then work out the number of moles of oxygen as 5.27 over 16, and I get 0.3295 mole. Right? So now I have carbon, hydrogen, and oxygen. I have the number of moles of each. I have 0.988. I have 2.64. And I have 0.32 or 330. Okay, so I have these three number of moles. I'm going to divide by the smallest, which happens to be this one. So 0.330 over 0.330 is equal to 1. 0.988 over 0.330 is equal to 3, and 2.64 divided by 0.33 is equal to 8. Okay, so I have a 1 to 3 to 8 ratio, so I have C3H8O. Right, and you should be able to draw a couple of isomers of this. Give it a go, but that's how you do it. All right, remember, I should have really saved this carbon, number of moles of carbon, this number of moles of hydrogen, so I could reuse it down here. All right, I should have saved this number over here as well. And I did save this number and this number to make sure that this number is correct. But you should be saving these numbers inside your calculator as you're doing the calculation. All right, now let's have a look at the next question. A 15.9 gram sample of organic substance containing C, H, and O burns in excess oxygen to form 31.77 grams of carbon dioxide. And look here, now we've got a little bit of different information for the water. So for water, we've got this information. The 12.7 litres of water at 200 kilopascals and 150 degrees Celsius. So this is water as a gas, and we've got a little bit of different information. Is that enough information to work out the number of moles? Absolutely. So it doesn't mean we can't do it. So let's go again. First of all, we'll work out the number of moles of carbon dioxide. Okay, 31.77 over 44.01, which happens to be 0.722, I think. Yep, 0.722 moles. And then I can work out the number of moles of carbon, because it's going to be equal to the number of moles of carbon dioxide over 1. And therefore, I'm going to save this value on my calculator as A. Okay? Now, to work out the number of moles of water, I have to try and remember what is my equation that will work out the number of moles of water given these sets of data. So I got a V, I got a P, and I got a T. All right? Hopefully you remember that N is equal to PV over RT. So P, 200. Volume, 12.7 over R, 8.314, times T. Now remember, T has to be in Kelvin, so 150 plus 273.15 is equal to 423.15 Kelvin, so times 423.15. Okay, so, and that gets me 0.722 mole. Right, let me just check that. I'm pretty sure that's what I'll get. Oops. Just remember to use brackets on your calculator, otherwise you'll get silly mistakes. And I'm going to save this as B over here. All right. Whoops, that's not what I wanted, because I don't want the number of moles of hydrogen, I want the number of moles of water. From the number of moles of hydrogen from the number of moles of water, it'll be times 2 over 1, so I'm going to times that by 2, and we get 144 moles. And I'm going to save this one as B. So I got the number of moles of carbon, I got the number of moles of hydrogen. Now remember, to get the number of moles of water, I need to work out the mass of both of those. So I work out the mass of C as 0.722 times 12.01. Isn't that great that I saved that value? A times 12.01, 8.70 grams. Right. And the mass of water will be B times 1.008, or mass of, hydrogen is going to be B times 1.008, which happens to be 1.456 grams. Now I can work out the mass of oxygen, which will be equal to the mass of the organic substance, subtract the total mass of the carbon. Oh no, Mr. Lim didn't change colors. How lazy of Mr. Lim. All right, and the mass of the hydrogen. So what's the mass of the organic substance? 15.9 grams. Subtract, bracket, 8.67 plus 1.456. Oh no, if only Mr. Lim had saved those values. I'm going to save that as D. And I'm going to save the other one as C. Okay, so now I have 15.9 subtract bracket C plus D, close bracket, and I end up with 5.77 grams of oxygen. Okay, Then I'm going to work out the number of moles of oxygen as 5.77 over 16, which happens to be 0.361 mole. And I'm going to save that to E. Okay, now I can work out the empirical formula. I have C, H, and O. I have the number of moles of each, so I have 0.722, I have 1.44, and I have 0.361. I will divide by the smallest, which happens to be this one, so 0.361 over 0.361 happens to be 1, 0.722 over 0.361 happens to be 2, and 1.44 over 0.361 happens to be 4. Okay, so now I have the empirical formula C2H4O. All right, so that's how you do empirical formula via combustion. All right. Once you have the empirical formula, you can work out the molecular formula via a molar mass information, which we'll make another video about later. Right? And then once you have the molecular formula, you can also work out possible isomers, and you can to work out which isomer it is, you'll need some reaction data, which we'll also make a video about later. Okay? So let's just recap. The goal is always to find the number of moles of each element. We're given combustion data. For carbon dioxide leads to carbon, the water leads to hydrogen, and then you can do a ratio if it's hydrocarbons only. For oxygen, you cannot solve it directly from the carbon dioxide or the water. Can I say that again? Because too many times people screw this up. The number of moles of oxygen cannot be solved directly from the carbon dioxide or the water. You must solve it via mass substitution. So that means you need to get the mass of the carbon and the mass of the hydrogen from the number of moles of the carbon and the hydrogen, subtract it from the original organic substance, and then work out the number of moles of it. Okay, that's it. Tomorrow you'll be doing lots of work on it.